In this video, we're going to talk about estimating a population mean. So if you remember back to our last video where we were talking about confidence intervals for a population proportion, you're going to notice some similarities when we talk about estimating confidence intervals for population means. Now, just like the last video, we were talking about population proportions, population means we will still construct a confidence interval for, because we don't know the population mean, right? We do all this work because we don't know what the actual average of the population's data value is going to be. So let's talk about a one sample t interval for a population mean. So notice that we're using t for mean and we use z for proportion. So there's definitely going to be some familiar stuff and some slightly different new stuff. So when conditions are met, which of course we'll talk about those conditions and they should also sound familiar to you, we're going to create a confidence interval of whatever that percentage is. Remember, 95% is the usual one, but we've seen as low as 80 and as high as 99. So we're looking for that unknown mean mu, and that is the population mean. Here's how we construct it. We have x bar, which is the mean of our sample, plus or minus this t star, which is very similar to our z star in a way, where t star is the critical value. So remember, z was the critical value for our population proportion. So t is for our mean, where we have n-1 degrees of freedom, which we'll talk about in just a moment, and we multiply that by the quotient of our sample standard deviation divided by the square root of n, or our sample size. All right, now let's talk about this t and this t star. So it comes from a t distribution, as we know, and that's not a standard normal distribution. So t star and z star have the same meaning in terms of our confidence interval. It measures how many standard deviations away we need to extend our point estimate, right, and our interval there, so that we get our desired level of confidence. So 95%, for example, we need to make sure that we have the t star that will give us that. So every single t distribution of our sample mean to get our population mean is going to be different, and that depends on the sample size. So for example, if your sample size was 3, your t value, or your degrees of freedom, which is what we call it, we do 3 minus 1, which is 2. So if we were looking at something like this, where this purple line here is our standard normal with a capital N distribution, and for example, if we have 2 degrees of freedom, or 3 is our sample size, we get this dotted red line here, which you may notice has a higher area on the ends and a lower area compared to our standard normal distribution in the middle. But if we increase our sample size to, say, 10, we would do 10 minus 1, so that gives us 9 degrees of freedom. That gives us this teal dotted line. And you might say, hey, that looks more like the standard normal distribution than, 2 degrees of freedom, and you'd be correct. Our area seems to be lower down here and higher up here. So the higher your sample size, the closer your degrees of freedom is going to mirror our standard normal curve. Something else that typically happens here when you increase your degrees of freedom, your sample standard deviation tends to get closer to the actual population standard deviation as well, which also traces its roots back to our normal distribution curve. So what if you want to find that critical value for your population mean, that t star? Well, I'm going to show you how to do that with your calculator. Nice and easy. So for example, let's say that we want to construct a 95% confidence interval based on an SRS of our sample size of 12. So what you're going to do on your calculator is you're going to hit second vars, that menu, and you're going to choose inf t, which is the inverse of t, which is exactly what we're looking for. We want that t star value that we're going to use. So if we have a 95% confidence interval and sample size of 12, we only need to enter in 2 things. And depending on your operating system, you might have to enter this in like this, or you might have a list to just enter in the things. But here's all we need to do. So we need to figure out the percent of one of the tails that's left over from that 95%. We did this before, it's nothing new. So we go 1 minus 0.95, that is 0.05 or 5%. We cut that in half, that's 2.5%. So that's what we enter. We enter in 0.025 there, and then we want our degree of freedom, which is this n minus 1. So 12 minus 1 is 11. Now that gives me a negative number. So really it is a positive value. Our t-star is going to be positive 2.201, but if you are entering it into that equation, essentially you're doing plus or minus. So the positive negative doesn't really matter, but if you want to be real specific here, it is actually a positive 2.2. Now let's talk about those conditions that we need to meet for constructing a confidence interval about a mean. 2 of these are going to sound real familiar, and the third one is going to sound mostly familiar, but it's a little slightly different for means. So we have to first make sure that the random quality is met. It has to come from a random sample. No surprise there. And then also our 10% condition needs to be met, where our sample is less than 10% of the whole population. Sometimes we have to guess about that, but we can use our logic brains to do that. And now the third thing is something that we call a normal/large sample. So that says that the population has a normal distribution or the sample size is large. So n is greater than or equal to 30. So if the population distribution has an unknown shape and we have n is less than 30, we have to use a graph of that sample data to assess if it is normally distributed or not. And so if it's not, we can't use our t procedures if it shows a strong skew either to the left or the right or has major outliers. Let's take a look at 3 quick examples to practice checking for that normal/large sample condition. So let's look at each of these 3 things and figure out, do they meet that condition? So first up, to estimate the average GPA of students at your school, you randomly select 50 students. Here's a histogram of their GPAs. Now, does that meet our condition? So looking at the sample size, first of all, 50 is greater than 30, so automatically, yeah, our condition is met, our third condition. And it's also plausible that the sample came from a normal population because the histogram doesn't have any kind of strong skew either way, and there aren't any outliers. So we have kind of a normal distribution here. So 2 things in the positive direction, we can say, yes, that condition is met. Second example is, how much force does it take to pull wood apart? The stem plot here shows the force in pounds required to pull a piece of Douglas fir, which is a tree, apart for each of the 20 randomly selected pieces. So does this meet our normal/large sample condition? So 2 things are against us here. Our stem plot is strongly skewed to the left here, right? We've got a strong skew, and there are possible outliers. And our sample size is small. It is not 30 or greater. So no, this does not meet that condition. Last one says, suppose you want to estimate the mean SAT math score at a large high school. So here's a box plot of the SAT math scores from a random sample of 20 students at the school. So does this meet the normal/large sample condition? So I'm going to say yes. Even though our sample size is small, 20 instead of at least 30, the box plot is only moderately skewed to the right and there are no outliers. So you can continue on with your t-star and all the other tests that you need to do. So there's no accepted rule of thumb for identifying strong skewedness, because that's the key there. I would say this isn't strongly skewed and there are no outliers, so I would continue on. But I would say that if you had something that you were on the fence about being strongly skewed and there were outliers, and you have a small sample size, I would say no. But in this case, we'll say yes. All right, let's put all this information together and construct a confidence interval for our population mean. So this one's about video screen tension. So the problem says, a manufacturer of a high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. So the tension is measured by an electrical device with output readings in millivolts, or MV. Some variation is inherent in the production process. Here are the tension readings for a random sample of 20 screens from a single day's production. So with this data and this information, let us construct and interpret a 90% confidence interval for the mean tension, mu, of all the screens produced on that day. So we got to do our 4-step process. First step is to state what it is that we're doing, and we are looking for the 90% confidence interval for mu, which is the true mean tension of all the video terminals produced on this day. Second step is to plan. So what are we going to do? We're going to do a 1-sample t interval test for mu, t because we're dealing with mean, and mu because it's the population mean. So 2 of the 3 conditions we'll talk about right now. One is it random? Yep, it's a random sample of 20 screens produced that day. Second, is the 10% condition met? Yes, assuming that 20 screens is less than 10% of all screens produced that day, so they have to produce 200 or more than 200 in that day. And our third condition is that thing that we were just practicing, the normal large sample. So I have this dot plot of all these data values up here. And so I'm looking to see, does it show strong skewness or outliers? And we have to take into consideration our sample size. So unfortunately, our sample size is 20, so that's less than 30, so that's small. But this dot plot does not look strongly skewed, and there doesn't seem to be any real outliers. So we're gonna say, yes, this third condition is met. So our third step is to do. So that means we're going to calculate our confidence interval using this equation. So we have X bar here. So if you wanted to put this into Statlet or into your calculator can give you your sample mean and your sample standard deviation. So I'm not going to go through all those steps to find that. So we have our X bar. And we have our S sub X, or standard deviation of our sample. We have our sample size, that's 20. So we now need to figure out our t-star. And how I find that is I use my calculator, I do inverse of t, and so I need the area and then my degree of freedom. So my confidence interval is at 90%, so that leaves me with 10%, and cut that in half, that's 5%. So I want 0.05, and then comma, my degree of freedom. So my sample size is 20, so 20 minus 1 is 19. And that gives me this negative number, but we're gonna ignore the negative, and it's 1.729132, yada, yada, yada. So let's plug all those values that we have in and figure out our confidence interval. So I plug in all my values here, and I get a confidence interval from 292.32 to 320.32. And the last thing that we have to do is conclude. So we are 90% confident that the interval from 292.32 to 320.32 millivolts captures mu, which is the true mean tension in the entire batch of video terminals produced that day. And of course, you can construct a confidence interval for a population mean on your graphing calculator. It's a beautiful tool. First thing that you would want to do is press your stat button, because duh, and then you page over to the tests menu, and then you choose t interval, because we're dealing with a population mean, so that is a t interval. And so on that screen, you're going to adjust your settings to, let's say, that previous problem that we were working with screen tension, and we choose calculate. So what you first have to do is you have to go into your list and enter in those 20 values that we had. And so when you do that, when you are in this t interval menu, you're going to select data, because you're entering in raw data, and you're going to use whatever list you put that data into. Keep frequency 1, and then your confidence level is going to be a value. So if it is 90%, you would put 0.9. If it was 95%, it would be 0.95, etc. You get the gist. And then you hit calculate, and look at this beautiful thing that it gives you. That was our answer. Gave us our sample mean, our sample standard deviation, and our sample size as well. Beautiful. And of course, if you are setting out on this journey to collect data of a sample for a larger population and you want to estimate your population mean, and you're thinking about, well, what size of a sample will make sense for that? Here is a rundown of how you do that when you are calculating mu, or your population mean. So to determine the sample size that will yield whatever confidence interval you are looking for again, our population mean, with a specified margin of error, because you should go into your surveying and your stats work with these things in mind. They won't always end up being aligned with what you plan for, but you got to plan for them. So first, get a reasonable value for your population standard deviation, sigma, from an earlier or pilot study, right? There's plenty of other surveys and things out there, so find something that aligns with what you're looking for. And then you want to find the critical value, so our z-star from our standard normal curve for a confidence level of whatever percentage you want. And then you're going to set that expression for the margin of error to be less than or equal to this thing. So our z-star times your sigma for your population divided by the square root of the sample size. So that calculation needs to be less than or equal to your margin of error. And a little note here, although we assumed a value for the population standard deviation sigma to calculate the required sample size, you should not assume a value for sigma when calculating a confidence interval for your population mean. So let's quickly look at an example of determining sample size from a margin of error. And this one has to do with monkeys. Who doesn't love a cute little monkey? So the problem says that researchers would like to estimate the mean cholesterol level, mu, of a particular variety of monkey that is often used in lab experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. So a previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. So what is the minimum number of monkeys that researchers will need to test to get a satisfactory estimate? So the z-star here, we want a 95% confidence level. I'm going to use my inverse norm and do half of 5%, which is 0.025 or 2.5%, and our classic 0 mean and 1 standard deviation, and we're going to make that a positive. So our z-star is going to be about 1.95996, or however you want to round it. And then our sigma, our population standard deviation, we're going to make 5. And we don't know n, so that's the thing that we're going to be solving for. And the margin of error is going to be 1, or 1 milligram per deciliter. So let's work that out. So when I plug in all my values, this is what my inequality is going to look like, again, solving for n. So another way to think about this is we have 1.96 times 5 all over the square root of n. So I'm going to multiply both sides by the square root of n. So I move that over here and I get things out of the fraction. And so next I want to get rid of the square root, and there's only a 1 next to it. So I'm going to square both sides. So that ends up giving me n is greater than or equal to 96.04. So we can conclude, we got to round up because we don't want 0.04 of a monkey. So researchers would need at least 97 monkeys to estimate the cholesterol levels to their satisfaction. I'm going to spare you my Owen Wilson impression with wow, but you made it to the end. Thanks for watching.